countless eruptions from the superflare on a young solar star.
Oh, thank you for introducing me and giving me the presentation opportunity. I'm Ikuta from the University of Tokyo. We investigated the dynamics of filament and prominence eruptions on a young solar type star, Ike Draconis, comparing with the solar one. For this purpose, we developed a simple one-dimensional hydrodynamical model based on a self-similar expanding loop of the solar ones. As you know, solar flares are explosions on the solar surface and observed in optical to X-ray wavelengths and driven by magnetic energy around active regions. Solar flares are sometimes accompanied by plasma ejections as filament and prominence eruptions and coronal mass ejections. Filament and prominence eruptions are cold and dense plasma, and CMEs are hot and rare plasma. Their typical temperatures are 10,000 and a million Kelvin, respectively. The solar CMEs were well modeled with the self-similar explosions of the magnetic groups. Stellar flares are also observed in optical to X-ray and driven by magnetic energy around active regions. We call flare with 10 to 1,000 times larger energy than largest solar flare, super flare. Recently, filament eruptions from a super flare were reported on a young solar type star, Ike Draconis, which rotates 10 times faster than the Sun, mainly from the spectroscopic observation of the H-alpha spectrum by CMS 3.8 meter telescope in Japan, simultaneously with the test. Right upper panels show the flare light curve by test, and lower panels show the light curve of H-alpha. You can see the H-alpha absorption during the post-flare. The variation in time reflects the dynamics of the filament eruptions. We show the dynamic spectra of H-alpha absorption for Ike Draconis in left and the solar one in right. Both are taken by telescopes in Kyoto University. The horizontal and vertical line axis mean time and wavelengths correspond to the velocity. Both spectra show similar temporal variations, and they are different in velocity scales. For Ike Dra, erupting filament had the velocity of 500 km per second as the blue shift, decelerated by gravity and fell to the surface. The terminal velocity is up to 200 km per second, observed as a left shift. For the solar one, same trend shows, and CMEs are associated, although its blue shift to correspond to 150 km per second, less than the escape velocity. Then the purpose is to explain the dynamic spectra of H-alpha spectral absorption using a model emulating the filament eruptions. Specifically, we would like to investigate how filament on Ike Dra fall and whether CMEs are associated with a super flare or not. Then we develop a model of the self-similarly expanding loop for falling filament. We formulate one-dimensional adiabatic equations in the rest frame of the loop, transformed from two-dimensional equations in the bipolar coordinate. The equations are based on the first paper by Professor Shibata. This paper was written 44 years ago. The loop configuration is described by in the right, and we need to tune the loop configuration parameters such as expanding velocity and initial height as described in blue. In addition, viewing angle and initial position of the filament are also important, and we are tuned these parameters. To calculate the model dynamic spectra, we assume that the mass with the certain velocity on the stellar disk and with 3,000 to 30,000 Kelvin correspond to the H alpha absorption under the optical thin condition. This is supported by the solar observation using a cloud model. Their typical optical depth range is from less than 1 to 10. Then this assumption is valid. We can derive the velocity along the loop from hydrodynamic equations in blue, and the velocity normal to the loop is set by hand to satisfy the induction equation of Maxwell equations. And this induction equation satisfies divergence-free condition of the magnetic flux tube. We can calculate the radial velocity to the line of sight by projecting the composite of these vectors. At the initial condition, we set intense density as a filament in part of the loop, and in other region, we set a rarefied density as a corner to satisfy pressure balance. First, we apply the model to the solar case. Left upper panel shows the reproduced spectrum by our model, and lower panel shows the observed spectrum. As you can see, the model is well reproduced with our sample model. In right panel, we show the expanding loop and trace the part of the filament in 2 dimensions. The trace of the filament is also overplotted on both spectra. In this case, the loop is observed from above. Yes. Then we can compare the spatial scales for the solar case. The right lower panel shows observable. The left panel shows the previous loop model, and the right lower panel shows observed filament eruption in H alpha image overplotted with our model. Until 5 minutes, spatial scale is almost consistent, and the model becomes larger by a factor of 2 over time. This is because our model is simple configuration, but valid to apply the filament eruption on Ikuta. Additionally, the expanding loop is less than the escape velocity on the surface, but the solar CME were associated with this observed filament eruption. Then corner on the loop not observed in H alpha can propagate beyond the escape velocity to reproduce the H alpha absorption. Then, second, we apply the model to larger filament eruption on Ikuta. Similar figures are shown, but the model spectrum is well reproduced in longer time and larger time scales than the solar one. Specifically, the loop length is so large, and we observe the filament inside the stellar disk from the viewing angle of 40 degrees. Stellar CMAs are expected to be associated because the velocity at the top loop top is so large, and larger than the escape velocity, which becomes escape velocity becomes smaller because the loop is higher, expand and higher. Next, and we also apply the developed similar model to the prominence eruptions. In this year, large prominence eruption on Ikuta was also reported as the H-alpha emission, comparing with the solar one, as well as the filament eruption. The dynamic spectra for Ikuta and the sun are similar to the spectra of the filament eruption. However, the H-alpha emission became invisible in H-alpha for Ikuta. Then we investigate the dynamics of the prominence eruption. Simply, the filament is observed on the stellar disk, and the prominence is observed out of the disk as stellar rim, shown in the right bottom pictures. Then we change the viewing angle of the model simply from the filament eruption. As a result, this result is preliminary, but we can reproduce the dynamic spectra of H-alpha emission for the sun viewing from the aside. We are working on the comparison with resolved image as in the solar filament eruption. Next. In addition, we apply the model to the prominence eruption in Ikuta. The spectrum of H-alpha emission is well reproduced for blue shift component. Then the prominence exactly hold. However, the temporal velocity of the model reaches 200 km per second because the prominence fall to the surface. Then the invisible residue thought to be due to probably velocity dispersion of the observation or to change the temperature of the prominence eruption to model this one. Then we need to observe the prominence eruption in multi-wavelengths to investigate the temperature dependency. This is the summary of my talk. We need to compare spatial scales of the sun for prominence eruption. We predict the solar CMEs only from the H-alpha spectrum within our model, and multi-wavelength observations are required to obtain reliable evidence in the future. After that, Kosuke talks about introducing observation studies for the eruptions I introduced. For M dwarfs, Yuta and Michael also presents as poster. That's all. Thank you for your attention. Yes. Yes. Oh, excuse me.
Repeat the question. Could you repeat the question?
How loop expand the slide? For the sun? Oh. Spatial scale is sorry, small number. Half solar radius. Yes. Oh yeah. Okay. Yeah. 50,000 kilometer we set. Sorry. Thank you.
Thank you. Can you hear me there? Yeah, is this working? Okay. Okay. Thank you, everyone.